Hi, this is Mr. Vincent, and today in aerospace engineering, I'm going to show you how you can use the data that you have for your NACA airfoils to construct a 3D inventor model, and then take that model and import it into the Cube Pro 3D printing software. So the first thing we're going to do is we're going to go to the East Engineering website, and from the East Engineering website, we will select the Aerospace Engineering tab, and we're going to scroll down, and we're going to select the NACA 4-digit airfoil tools. We're using the 4-digit. There are 5-digit. There's NACA 6-digit as well. We're going to use the 4-digit today. They're a little less sophisticated, but it'll also be certainly well enough to demonstrate how to pull the data in and construct a physical model from the data. So on the NACA 4-digit airfoil generator, you can see on the screen there is a airfoil profile, and we can scroll down, and it in this part of the screen, it shows us what the 4-digit airfoil specifications stand for. Each of the 4 digits has meaning. So if we look at the NACA 4-digit, if we break the 4 digits into the first one being an M, second one a P, and the final 2 XX, each one of those has meaning. The first one, M, is the maximum camber divided by 100. For example, if the M is a 2, it would be 2 divided by 100, or 2/100ths, or 2% of the chord. So that's the maximum camber is 2% of the chord length. Remember, the chord length is the straight line from the very leading edge where my cursor is, straight line to the trailing edge. So the maximum camber is 2% of that overall length. The second digit, the P, is the position of the maximum camber divided by 10. And that position is from the leading edge. So in this example, P equal to 4 would be a position of 0.4, or 40% of the chord from the leading edge. So if this is, let's count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A second digit of 4 would be 40% of that, or 1, 2, 3, 4. So it's at this location, 40% from the leading edge, that we would find the maximum camber. The final 2 digits are the thickness divided by 100. So for example, if it's a 12, the thickness would be 0.12, or 12% of the chord. So all of these values are relative or in some relation to the chord length. So the thickness divided by 100 gives us 12%. So that would be the thickness. And again, that maximum thickness would be right here at the 40%. So this is the data, and this particular one is a NACA 2412. If we scroll down to this region right here, it shows us all of the NACA options that we have available. There are several options. I'm going to, for the purposes of this demonstration and exercise, I'm going to discourage you from doing any of the NACA numbers that begin with a 0, just because they're not as interesting. They are certainly valid airfoils and have an important function in the world of aerodynamics, but from an interest standpoint, we're going to stick with some of the others. I'm going to go ahead and look at a NACA 4415. So 4415. Now, if we want to know what kind of airplanes would use that, we could go back to our engineering website, our aerospace engineering website, and we could call up the page for incomplete guide to airfoil usage. So let's click on that and open up this window. And I'm going to make it a little larger. And if we scroll down, there's a lot of good information on this, including what NACA stands for. The acronym NACA stands for National Advisory Committee for Aeronautics. But if we scroll down, we quickly get to a place where we have a lot of information about different airplanes. These three columns contain information. In the left-hand column, we have a list of airplanes, and then in the two right-hand columns, we have information about the airfoil. I'm going to take my slider bar on the right-hand side and just pull down, and you can see that there are quite a few airplanes listed. Now, this is considered an incomplete list. Why? Because there are always new planes being produced and data being collected, and any list that you make will quickly become obsolete. So the creators of this list recognize that it is incomplete. But let's see if we can find airplanes that use the 4415 NACA two-digit number. So I'm going to push Control F for find, and I'm going to type 4415. And I can see in the results that there are 173 airplanes that use the 4415. So we can scroll down and they're highlighted. There were 3 up above. Here's a long list. Air Tractor AT301. I'm just going to do a copy, and I'm going to open up another window and paste that. And let's see what kind of an airplane that is. So here are images of an Air Tractor AT301. This is an example of a plane that uses the NACA 4415 airfoil on its wings. So just to give you an idea, for your exercise, you're actually going to research some of these planes and record some of the data that would be used, and the manufacturer and some of the important history. But let's go back to looking at these specific airfoils. So I'm going to select 4415, NACA 4415 from the airfoils tool. And you can see it displays the profile, the cross-sectional view of the 4415 airfoil. Now, if we want to collect the data that describes that airfoil, we would we would select the link Send to Airfoil Plotter right here. So I'm going to select that, and it is going to give us some more detail. I want to point out that the chord length listed is 100 millimeters. Now, when we use this data, we're actually going to convert it to inches, but having it as 100 millimeters is not a disadvantage at this point, because the chord length, it measures from one end to the other. So it starts at 0 and goes to 100 millimeters. We could easily view that as 100%. And when we get our data, we can simply multiply it by whatever number we need to convert that to inches. I'll show you how to do that in the spreadsheet. Now to download the data, we're going to select the CSV file. CSV file of coordinates, and that is downloading a CSV file. What is a CSV file? Basically, a CSV file is a spreadsheet without all the formatting. We can open this up. As a matter of fact, it will automatically open it up into Excel if I double click on this link, and I'm going to do that in a moment. But a CSV file has none of the formatting. So I'm going to go ahead and double click it, and you can see it opens up the NACA 4415 file in Excel. And we have our data, and I'm just going to double click. I'm going to select the line between the columns A, column B, and double click so that it makes it fit the data within those columns. And we can see that the chord length is 100 millimeters. So I'm going to now clean this data up. So we have the airfoil surface. That's what we want. We don't need any of the data above that line. So I'm going to select the rows up to row 9 where it says X values in millimeters and Y values in millimeters, right mouse click and delete. So I cleaned up that data. And I'm going to scroll down and I'm going to keep scrolling, and then where it provides camber data, we don't want the camber data either. So I'm going to delete that, and I'm going to right mouse click delete, and that leaves us with only the data that we're interested in. Now, I want to convert this into a 4-inch instead of 100 millimeters. I want to convert it to 4 inches. So in order to do that, I'm going to set up a formula, and that formula is going to be equals, and I'm going to select the first cell, A1, then I'm going to put a forward slash, which is divide by 25.4, because there are 25.4 millimeters in an inch. And I'm going to select enter. So what that will do is that'll convert the 100 millimeters into 25.4. Now, I want to do the same thing to all the values in columns A and columns B. To do that, all I have to do is select the cell D1 and then select, there's a little box in the lower right-hand corner. If I position my cursor over that box, it turns into a crosshair, and I can drag that down. Actually, I'm going to drag it over, and then I'm going to drag it down. Too far. Let's go back up. And it automatically converts those numbers that were in millimeters into inches. What I'm going to do now is, while that entire column is highlighted, all the converted data is highlighted, I'm going to right mouse click and I'm going to do a copy, and I'm going to leave that data, that highlighted range highlighted, and I'm going to do a paste special, and I'm going to paste the values, not the formulas, the values. So what that did is that gave us just the values without any relationship to this original data. So I can now go back to the original data and I can say delete. And our original data gives us the X and Y values for all the points. I'm going to go ahead now and do a file, and I'm going to do a save as. I would encourage you, I'm going to do it in, place this file in my downloads. You're welcome to do the same thing, but I would encourage you to, at some point in this process, upload whatever files you create into your Google shared drive. I'm going to just convert this into the downloads and save it there. So I'm going to select downloads. And the other thing I'm going to do is I'm going to save it as not a CSV, which is comma delimited. I'm going to save it as an Excel workbook. So we're saving that data as an Excel spreadsheet. So at this point, what I would like to do then is open up Inventor. I actually have Inventor opened in another window, and I have another airfoil there. I'm going to start a new one though. There's an airfoil I made earlier. I'm going to do File, and I'm going to select New. and I'm going to select standard IPT. IPT is the extension for inventor part file. So I'm going to make a standard inventor part file. And I'm going to start a new sketch. And I'm hovering over the planes. I like working in the XY plane. Could do it in any one, but I like working in the XY plane. And that gives us it starts a 2D sketch. And what we want to do now is we want to import the points that we just transferred over from the Airfoil website into the Excel spreadsheet. So I'm going to come over here to insert points. I'm going to select that. And in downloads, here's our file. It's the NACA 4415 that we just created. I'm going to go ahead and double click on that. And it imported all those points. So I'm going to go ahead and hit the home button. And you can see, and I'll go ahead and hit the front view. There is the front view of all the points that we just created. And that now they're imported into our inventor file. What we want to do now is connect those points into a closed loop so that we can extrude a 3D model of that airfoil. To do that, I'm going to select the spline tool. So I'm hovering over, and you can, when you hover over an inventor, it tells you what that tool will do. This will make an interpolated spline. So I'm going to select that. Now I'm going to zoom in, and I'm going to start selecting points. I'm going to start right here on the lower portion. It really doesn't matter where you start, but I'm going to start on the lower portion, and I'm going to carefully, one by one, select those points. How do I know that they're selected? When I hover over them, the point gets a darker green shade to it, and that means inventor has snapped to, it recognizes that as a point, and it snaps to that point. So even if I'm not close, it will snap to it. I'm zooming in a little bit more and carefully selecting. You want to make sure that you're selecting. I'm going to hold the scroll wheel down and move, and then I'm going to go back and select. If you do misselect, you can go back, and here I'll misselect right now. Oh, I didn't want to select that. If I right mouse click, I can select back, and it'll eliminate that one. So there's my point. Wish I could fast forward through this. This is a tedious process. I don't remember how many points there were, but there were quite a few. So there's really, I wish there were a shortcut through this, but unfortunately there is not. Scroll out to get a bigger picture. I inadvertently hit select, which means that I ended my my spline, but I didn't want to do that. Let's see if I can start a new spline. It let me do it. I'm not suggesting that that's the ideal, and I'm glad that it happened on a relatively straight segment of the spline. And I continue to select. It's a little easier on these segments because the checkbox does not get in the way. I think when we make the turn here soon, it may get in the way. There are some tricks that you can use to avoid that problem as well. And I'm going to go ahead and try that. I'm going to go ahead and rotate our model so that the box is on the opposite side. So I'm connecting the dots from the other side of our sketch now. And again, I recognize that this is tedious, but it is very important. And I encourage you to make sure that you have the bright green light on the points, meaning that Inventor recognizes that you're selecting that point and it's going to snap to it. All right. So we have connected all the points, and I'm going to finish sketch. And I'm going to select the home that puts us into that orientation. Then I'm going to extrude. Now that's always a good sign when you select extrude and it starts to extrude, because extrude will only work if you have a closed loop. And there's always a concern when you're selecting points around the loop that it may not be closed. But I see that it did close, so that's a good sign. And in the default extrusion is 1 inch. I'm going to extrude it 4 inches. I'm going to zoom out, and there is our airfoil. I'm going to select OK. And if I hold the shift button down and the scroll wheel down, I can rotate it and admire the extrusion. Now, I'll hit the home key to give us an isometric view. Notice that there's a line across the top and a line across the bottom. What that reflects is that this is actually a construction of 2 separate splines. Remember, halfway through, I made a mistake and ended one spline. I was able to pick it up and continue on. And especially because it was in a relatively straight section, not in a high curve section, it blended well, but Inventor still recognizes that there's a transition there. So at this point, we have our 3D model, and we are ready to save it. I'm going to go ahead and do a file, save as, excuse me, save as, and we will call this the 4415, let's call it the NACA 4415 airfoil. And we'll save this in the inventor's parts list. And what I'm going to also do then is I'm going to do a file, and I'm going to export. And this is how you make the file that can be brought into your 3D printer. We're going to make an STL file. So that is going to be I think that's the CAD format. Let's take a look. Yes, STL files. There it is. I'm going to, so it's going to save it as a NACA 4415 airfoil as an STL file. I'm going to save that. And that file was saved. And now I am ready to import that file into our Cube Pro post processor that'll convert the standard STL file into the Cube Pro format that will be necessary to perform the 3D printing. So I'm going to select the Cube Pro software, and there's already a file on there from an airfoil I did earlier. I'm going to go ahead and clear that. So I'm going to close that model, and I'm going to go open up a new model. And I'm going to go to my inventor. Actually, I forgot where I saved that file, so I'm going to go to File, Save As, and it's in the Aerospace Frame Analysis folder, so I'll go look there. So I go back to the Cube Pro, and I go to my inventor folders, and it's in Frame Analysis. And there is the NACA 4415 Airfoil STL that I just created a few minutes ago. I'm going to open that, and it's giving me a warning. Let's see, 3D verified, determined your STL file is bad. Do you want to open it and continue with the 3D fixed STL file? Okay, let's do that. Is the model in millimeters? No, it is not. STL is bad and may not print correctly. Okay. Well, there is the file that it placed on there, and I'm going to rotate it. There's our airfoil sitting on the plate. It appears to be good. It may not have liked the fact that the splines were merged, but it appears to be a good file. Let's go ahead and try it. It looks good. That's where I want to place it on the plate. So I'm going to select build. And this is actually building the code to generate the 3D print. The standard offerings are good. The layer resolution of 200 micrometers is fine. Almost solid is fine. And the internal pattern, the honeycomb pattern is fine. So I'm going to select build and let it put the build file in the same place, the AE frame analysis, as the other files. So it's building. And when it builds, it actually constructs it. It's called slicing. And it constructs it and creates it slice by slice or layer by layer, because that's the way 3D printing constructs the model. It lays down a layer and then lays another layer on top of it, and then another on top of that. So it said the build is complete, and the estimated build time is 3 hours and 34 minutes, and it will require 74 grams of material. We'll go ahead and try that. The software is good from a standpoint that it tries to anticipate problems. I suspect the problem that it thought it might have was the incomplete splines, but I think that will work for this particular model. So I'm going to select yes. And we can now see it now has, I'm going to zoom in, and you can see the 3D model printing of it. So at this point, what I would do is I would transfer this file to a USB drive and plug it into the Cube Pro 3D printer and print it. I'm very confident that it would print properly. Again, the warnings that it gave, I think, are related to the two spline segment. Of course, if that were to be a problem, what we would do then is we would go back and be very, very careful in our point selection to make sure that we didn't close our spline too early. Hope this helps, and happy 3D printing.